And thank you for joining our Expert Hour Masterclass on space sciences. My name is Rupali Verma, and I work as an advisor with Education USA India. I can still see a lot of students who are entering the waiting room. We are admitting them as and when they are coming. We'll just wait for another 2 more minutes till the time students are joining. In the meanwhile, all the students who are already in and can see our screen, um, there is a chat box, and if we'll request you if you can quickly write which city you are joining us from by typing it in the chat. We would love to see how far our audiences span today. We tried to reach out to lots of universities and colleges for this session, and we really want to see which city are you people joining in from. So please write the city in the chat, and we'll come to know which part of India are you joining us from. And the ones who are again joining us, it will also be good if you write in the chat as to what comes to your mind when you hear the word space. Since it's a space science masterclass, before the professor joins us, if you can just write down what comes to your mind when you hear the word space, you can just write the word in the chat. Okay, there are a lot of words coming. Do write the city where you are joining from. Do write one word that comes to your mind when you hear the word space. Okay, so without taking too much time, um, let us start with the session. And I can see the words like stars, NASA, black holes, galaxies, and that's what is the beauty of space. It means something which is different to everyone. So today's session is also an opportunity to go beyond these words and discover the science, research, and opportunities that actually make space science one of the most exciting fields today. Some housekeeping rules. We have already started, and just make sure that your camera and your audio are muted. Actually, we have muted, but just in case, if anyone is, if you see any, just to make sure that to avoid any distraction, just keep yourself muted. You can post your questions in the chat box. After the session is over, we'll give you time to have the questions in the chat box. Um, Make sure that you keep your questions relevant to the session because it's just a 1 hour session and we want to have maximum out of it. Use headphones for your enhanced audio quality and check out the resources that we'll keep posting throughout the session in the chat box. Many of you, I'm sure, are attending the session for the first time. The ones who have attended our sessions in the past, they actually know about Education USA, but for the ones who are new, just let me tell you that Education USA is your official source on higher education. And we are also a US mission supported platform that advances US leadership in higher education, research, and innovation while promoting lawful and responsible academic engagements with the United States. We are headquartered in New Delhi with an advisor in Mumbai. Um, if, if you want to sign up for attending our future sessions, stay connected with Education USA. Here is the QR code. You can also follow us on social media platforms. on YouTube, Instagram, Facebook, Twitter, and do check our website, which is educationusa.in. The agenda is we'll have the tutorial in space science for 35 minutes with Professor David Alexander, and then there will be an overview of research and opportunities in space science in the United States, and then we'll open up for question answers. So for our expert for today is Professor David Alexander. So Professor David Alexander is an astrophysics professor at the Rice University, director of Rice Space Institute, and a faculty scholar at the Baker Institute of Public Policy. He is internationally recognized space scientist who was awarded the OBE, that is the Officer of the Most Excellent Order of the British Empire, by Queen Elizabeth II in 2018 for services to the space industry, and also holds a National Order of Merit by the French Republic in 2026. Professor Alexander has served on several prestigious NASA advisory committees and currently contributes to key aerospace and space economy initiatives in Texas. He earned his bachelor's degree and doctorate from the University of Glasgow. So over to you, Professor. I'll stop sharing my presentation and you can start with the session. 1 second. Yes, Professor, you can start sharing your presentation now. Students who have
Thank you,
joined
Rupali.
us, I would just like to tell you that we have with us Professor David, who's sitting right now in South Korea, and it's almost 9:30 p.m. there. We are also joined by Jennifer Hunter, who has logged in from Texas, which is early morning there, and I am right now taking this master class from New Delhi, and it's around 6 p.m. here. So over to you, Professor.
Thank you. I'm hoping everyone can see the screen already. If Rupali, can you see the screen? I don't know if Rupali went
Yes,
to mute,
yes,
but hopefully you can see the.
yes, I can.
Okay, great.
Yeah.
Well, thank you for the invitation and the opportunity to speak with you all. Space is really kind of big, and so there's a lot to talk about, and 35 minutes is probably not enough. But because I'm given some of the words that you put into the chat, there seems to be a lot of people interested in science. So I will talk a little bit about science, but there's also other opportunities within space across the board on the engineering side, but also on the social sciences and the humanities side. And I'll touch on a couple of those things as we go. But we have a lot to get through, and I want to make sure that there's time so that you can ask some of your questions. I can't promise to answer them all, but I will try. So I wanted to give you a little bit of insight. Jennifer's going to talk a little bit more about Rice University at the end. I'll talk a little bit about the Space Institute. But when it comes to space, one of the things you really should know is it kind of not space itself, but our current space program really started, it got moving back in 1962 at Rice University. There's a very famous speech by President John F. Kennedy that he gave at the football stadium at Rice on September 12, 1962. And that basically, there was a big race in those days to beat the Soviet Union, as it was then called, to the moon. And the president committed the United States to doing that within 10 years, within the decade. And as most of you know their history, they managed to do that. And so that speech that committed the United States to doing this and created the Apollo program and so on started here at Rice. So we've a long and a proud history of working with the space program in the United States. And then also the Johnson Space Center, which is the home of human spaceflight, is located in Houston. And a lot of that has to do with Rice as well, but I don't have time to go into the whole history. I'm not going to read all of this, but this gives you a sense of some of the connections that we've had We have a moon rock at Rice that was given to the Kennedy family, and the Kennedy family turned around and gave it to us. If you look on the bottom right, you'll see the number 60. That's the actual football field. I think it's been returfed since the 1960s, but that's the football stadium in which Kennedy gave his speech in 1962. And in 2022, we hosted an anniversary event. Rice University and NASA put on a big event. And what you're looking at is 700 people spelling out the number 60 on the football field. At the same time, picture was taken by a drone, but at the same time, we took a picture from space. And you could do what was called a space selfie. So we had a lot of fun, and it was just as hot that day as it was in that day in 1962. So it was, if you were out in the sun, it wasn't all that pleasant. So what I want to do is talk a little bit about what I think is interesting about space, and it's a whole range of things, and I'm going to give you a cursory view. But since most of you are students and you're thinking about the space industry, I wanted to tell you just quickly. So I don't know if you can tell from my accent, but I'm not from Texas. I am actually from Scotland. My degrees are from the University of Glasgow, and I'm from the city of Glasgow in Scotland. And the reason I mention that is because all of my education, actually, at least the formal education, I got in the United Kingdom. And then I was a researcher for a few years before I moved to the United States. And so there's that international connection back to the United States. And when I came to the US, I went to one state, Montana State, to help start a program there. And then before I came to Rice, I was actually working for Lockheed Martin, designing missions to study the sun and doing the science on those. So, and then I've been a professor at Rice for the last 23 years. So I've been in the United States for a long time. But the message there is you don't have to always get a PhD. You don't always have to go to university. You can actually go to industry. And I'll tell you a little bit more about how that's changing today compared to when I did it a long, long time ago. And the path, each one of you will find your own path. And the path that you'll find will hopefully be the right one for you. And it doesn't have to be cast in stone right now where you say I have to do this. Some of you might want to be astronauts, and I know that India is pushing forwards on a human space program. So there's lots of different ways that you can be part of space, either at a university, in industry, in a not-for-profit, in government, all sorts of different ways. And we're going to touch on some of those things as we go through, and we can maybe address some of them in the questions as well. So I'm going to start a little bit with the Space Institute very briefly, and then talk about different aspects of space, at least the modern version of space. So what we do at the Space Institute is we try and provide opportunities for our students, undergraduates and graduate students, and our faculty. Rice does a lot of fantastic research in many different disciplines for different for the energy sector, for life sciences, for healthcare, for social sciences, for the whole range of things. Um, and what we try and do is bring some of that research into the space world. As I hope you'll learn over the course of the next half an hour or so, we need everything to do what we're trying to do in space. We need medical technologies to keep our astronauts alive. We need power technologies. We need propulsion technologies. We need new materials. We need people who can tell stories to get the science out to everyone and why what we're learning. And so we really need every skill that we can. And so what we try and do is look at what Rice faculty and students are doing, and then find a path to make that apply to space. Generally speaking, we always have to have a vision and a mission, but the bottom line is that we want to, our focus, and I'll talk a little bit about this later as well, is our focus is on um, essentially life. We're trying to understand on the science side, we've got a big focus on star and planet formation, planetary evolution, and then how stars and planets interact. Many of you probably know that we've found planets around other stars, and so we're trying to learn uh, we're trying to use what we know about the sun and how it interacts with the earth, and then how we can apply it to these new systems. But because we're in Houston and we're heavily connected with NASA and human spaceflight, we're also trying to work on the engineering and science side to think about how we can support humans in space, how we can keep our astronauts alive and working in microgravity, how we can keep them alive and working on the moon, and then ultimately to Mars. I'm going to show you that as we go. So the other key thing there is we're a university, and Rice is a very strong undergraduate institution where there's a lot of focus because of its size. We're not very big, but we're small but mighty, I think is the phrase. We have some very, very good students from all over the world. And so what we want to do is create that, not just get people degrees in science and engineering and English and so on, but to actually make them leaders in their field. So our role in the Space Institute is to try and help generate that next generation of leaders in the space science, the exploration, and then everything that goes around to support all of that. So that's our key mission. And I'll talk about a couple of these things later, but we do that. Obviously, research is a big part of what we do. Rice University is a what's called a tier one research university. Lots of fantastic work going on in very many different disciplines. As I said, so materials, artificial intelligence, robotics, a whole bunch of different things. The faculty and student engagement I've already mentioned. We work with industry, and I'll talk a little bit. I'll be focusing a little bit on industry as we go. And of course, we're an education and public outreach institution. And then, because of my background, one of the things that we do, and which is why I'm very happy to be talking to all of you, is the international engagement. I mean, as Rupali mentioned, I'm in South Korea right now attending the Korean Space Summit, but I'm actually here as a guest of the Swiss government. And so I was part of the Swiss delegation in Seoul last week. And then we work with countries and people in different countries across the world in many different ways. So that's the kind of key essence. And all of this, the students, the faculty, the research, the international partnerships, the industry, all of this is needed if we're going to succeed in what we're trying to do in space, whether it be for science and studying the universe, or whether it be for exploring the moon and finding water to help power spacecraft in low Earth orbit, all those things that I'll touch on. So I often get asked, and I know I'm probably already running over time because when I talk about space, I get very enthusiastic about it. But I'm often asked, there's a lot of problems that we need to solve on the Earth. And so I often get asked, what is the importance of space? And each person has their own interest and their own sense of what they might think is important. But I try to capture it in what I call the four eyes. Um, the key thing that we use space for in our everyday lives, I'm sure we're using space probably right now as we use satellites to convey this information, and that is that eye, that information. And so we can learn about the environment from space. We can learn about, uh, we can use it for transportation. We can watch ships cross the Atlantic or the Pacific or the Indian Ocean. And so we actually use space very much for information from satellite navigation, financial transactions, a whole range of different things, not just on the science, but in operating businesses and so on. The other thing is innovation, and I think this is I'll touch on this again in a second. If you think about the space station has had a human on board, at least one human on board, for for almost 26 years, which means that for most of you, or for all of your lives, most of you, if your parents are there, they're probably a little bit older, obviously, but for all of you, there's always been a human above your head. There's always been a human in space for your whole life. And that means that we're becoming essentially a spacefaring species. We're no longer stuck to planet Earth. And in order for that to happen, in order to keep those humans alive, the scientists and engineers have had to be innovative. Um, cleaning the water, reclaiming 97% of the water on the space station, International Space Station, is reclaimed water. The astronauts talk about yesterday's coffee being tomorrow's coffee. I'll let you think about what that means. But basically, that innovation, how we generate power, how we clean filters, how the astronauts get to walk out in spacesuits, all those different things. The other eye is the imagination. If you can do this, you can imagine that you could almost do anything, and you can come up with your own examples. I've got a couple of little things about mining on Mars and then building a power station or a solar power station in space to solve all of our energy problems. But in America, and I think this is true over the world, when we're trying to solve a major problem and trying to think about how we might, for instance, cure cancer and things, we often call it a moonshot. And that goes back to that speech by President Kennedy at Rice in 1962. So you can imagine if humans can do this, what can't we do? We should be able to solve some of the world's problems if we all put our minds together and our effort together on that. And that's where the imagination comes in. And then the other part, even though I like robots, and we've got robots on Mars, we've got robots on the moon, we've got robots in orbit around the Earth, um, humans allow us to see ourselves in this activity. And so that inspiration, it always sounds a little bit nebulous when we talk about it, but you can see yourself in that person, that person who walked on the moon or went to the space station or ultimately will go to Mars. And you won't care what country they come from. If the first person on Mars is from India, the whole world will celebrate. And so I think this something that is really important because it inspires the younger people, not necessarily to become astronauts, but to think about how you can solve real problems and do anything that you put your mind to. And so this is something that's really important. So I try and capture this is how I see space. It's these four eyes. It's this thing that captures all of the aspects of it that allows many of you are here because you're interested in space, and you're interested in space probably because of one, if not all, of these four things. Now, when it comes to innovation, this is something where, for those engineers amongst you, those of you thinking of going into engineering and thinking about space exploration, you cannot go to the store in space and replace, your batteries or replace your bedding or, you cannot do that. We do resupply the space station, but as we go to the moon and as we go onto Mars, that becomes a little bit more challenging. And so what that means in my mind is that space is a low resource environment. We can get energy from the sun, and that's about it. If we go to the moon, we might be able to get water, but it's a low resource environment. And if it's a low resource environment, you have to be clever. You have to be innovative. You have to think of solutions that can be done with limited resources, limited materials. And if you can solve those problems, remember there's humans involved here on the space station. If you can solve those problems that allow that human to be healthy and to survive the harsh environment of space, then there's 8 billion people on the planet that will benefit from those technologies and those ideas. And so this is the bigger picture. It's not just about going to space to go to space. It's about solving challenging problems and then bringing that back to benefit the people back on Earth. Since those are the people on Earth are the ones who are paying the money to send these astronauts to space, but a lot of the work that gets done in making that happen, benefit all of us here on planet Earth. So this is a key element I would like to also emphasize because you could argue that we go to space to do science, but in order to do that, we need to have the engineering. And so the science and the engineering comes together. And if we're going to tell that story, that's when we need the humanities and the social sciences. So it really is everything, the arts and so on. So again, I want to leave you with that message. If you don't remember anything else, remember this one. And one way to think about that is think about the technologies that you might use if you were trying to be an astronaut or if you needed to have a spacecraft or a satellite or a space station or a habitat on the moon. You would develop some technologies to allow you to do that, and then you would translate them to the ground. And I've listed some things here. You could put your own list together if you wanted. And then the other thing too is we're already doing a bunch of stuff on the Earth, and some of that AI and machine learning, for example, is a classic one, that can be translated to help the astronauts and the satellites in space. But the key thing is here is that these lists are interchangeable. It's not space separately from the Earth. It's the two together, and we learn from each other. We learn by solving a problem on the Earth, perhaps for in a hospital. We learn from that technology and then apply it to the astronauts on the space station. If we need to monitor the health of an astronaut in the space station, and we don't have the means to take up a hospital, we have to miniaturize the hospital. We have to take those devices up and make them be effective. If you can do that because you have to for space, that then becomes a great tool for hospitals on planet Earth, for example, where you've got limited resources, or you need many of them instead of just one big one. So you think about these as solving problems, not about solving space problems or Earth problems. So again, that's that innovation side. Now, I know I'm running. I don't have a clock in front of me, so Rupali is going to be pulling me shortly. Right now, we're focused on the Earth, very much so. I've been talking about the space station, and we're talking about satellites in low Earth orbit. I'll talk about the bottom right picture, which is in orbit manufacturing. I'll talk about that in a second. We're really focusing in Houston and many other countries and thinking about the moon. And of course, India has a proud heritage, recent heritage, but still very successful heritage with the moon. The Chandrayaan missions to the moon were very, very successful, and India led the way with those. In fact, India was the fourth country to do a soft landing on the moon, but they were the first country to do that at the South Pole. South Pole was a very interesting area of the moon, which I won't have time to talk about, but it's a very hazardous place to land. And the Chandrayaan 3 mission, I think in 2023, so a few years ago, landed there. So again, there's a lot of opportunities in India with the Indian ISRO, Indian Space Research Organization. Fantastic organization doing a lot of really cool things, including being the first country who had a successful orbit insertion around Mars. Every other country's had many failures, and particularly the first one. India made orbit successfully in their very first mission. So again, there's a lot going on in your own country and then partnering around the world. Now, ultimately, we want to get to here, and we're using the moon as what NASA calls a proving ground. We're trying to test our capabilities, test our technologies at the moon so that ultimately we can send humans to Mars. This is a fake picture, as you could probably. I'm not very good with AI, so I just stuck another picture on top there, but you guess you get the message. So as I think about the different aspects of space, one of the key elements, this is a kind of very difficult to read picture, but it captures all of the missions that NASA, in many cases, have in partnership with other countries, have created to study the universe. I was brought to the US because I was interested in studying the sun, and so we have a number of missions that look at that. There are many, many missions that study the Earth, and we've sent robotic and telescopic observations, satellites to essentially most of the planets in the solar system. Mars is obviously very important with the rovers on Mars, but we've sent missions to Jupiter. There's a mission right now on its way to a moon of Jupiter called Europa. It's called the Europa Clipper. You can sort of see it there. And Europa is a moon that it's very, very far away. It's 5 times as far away from the sun as the Earth is, but it seems to have an ocean under a sheet of ice. And one of the things we get excited about when we know there's liquid water is potential presence for life. We're still looking for signs of life on Mars. We haven't given up. But there's a mission to Europa, and there's moons of Saturn, Enceladus in particular, that also has water in its interior. And there's a lot of organic material in the solar system. And so, we're looking for life in the solar system. We're also looking for signs of it around other stars. And then, of course, we're studying black holes, we're studying quasars, we're studying other galaxies, we're studying star formation. The James Webb Space Telescope, for example, is doing amazing things. So this is the big science picture. Very, very important, teaching us about our place in the universe overall. And I'm going to try and I don't have time to go through. I could give you 2-hour lecture on every satellite there. And hopefully the music's not too loud. In the next 30 seconds, you're going to see everything. You're going to have everything you need to know about solar and activity. This is the sun. This is our nearest star. You see the small flares. You've got a massive. Okay, so that's the sun. And a couple of things here. One is because the sun is it's still quite far away. It's 150 million kilometers away, but it's a star. But because it's closer than any other star, the next nearest star is about 36 trillion kilometers away. Um, we can get a lot of information about this star. And we can learn a lot about other stars by studying this star, by studying the sun. We can also learn a lot about the fact that it interacts with all of the planets in the solar system. And so the next movie is going to show you what happens when that activity from the sun, you saw solar flares and coronal mass ejection. This is what happens. Some of this is modeling, but this is what happens when it gets to the Earth. All right. Well, I'm not going to give you a quiz in any of that, but what you're seeing here is particles from the sun. The sun sends out radiation, both photons, which is electromagnetic radiation like light, but it also sends out a lot of very fast moving particles, and they interact with all of the planets in the solar system. Now, the good thing about us on the Earth is that we are protected from that radiation by the atmosphere. That stops the photons, and we're saved from the particles by the fact that the Earth has a very strong magnetic field. Even the space station that you can see here is somewhat protected by the Earth's magnetic field. You saw some radiation belt stuff. You're looking at the aurora here. Now, what this tells you on the science side, we're trying to understand all of these phenomena. How do you create aurora? What happens? What causes the sun to erupt and create flares and so on? But all of that radiation is covering all of space in the solar system. And once we leave the Earth's orbit, once we go far enough, even just to the moon, we're in real trouble, especially if we send humans, because space does not have the magnetic field to protect us. It doesn't have an atmosphere to protect us, the vacuum of space. The moon doesn't have a magnetic field and it doesn't have an atmosphere. Mars has a kind of crazy little magnetic field in the southern part of it, but it doesn't have a planet-wide magnetic field, and it has a very, very thin atmosphere. So if we're going to go and explore away from the Earth, we have to worry about what the sun does. We have to worry about what that radiation environment looks like, not just for humans, but also even if we send robots, the electronics can be have some problem. Again, that's where the engineering comes in. And again, we can learn from the sun about stars. We can learn about how the sun interacts with the Earth, about the Earth, but we also can learn about how stars and planets interact. And that's what we use. So some of the work I'm doing at Rice, that's what we use to try and understand whether some of these new planets that we're finding may or may not be habitable. If you're an astronomer, you want liquid water. If you're a space physicist, you want magnetic fields. And we don't, with some of these planets, in order to find them, they're very close to their star. And the stars look just like that movie I showed you about the sun. If you're too close to that, that's not good for habitable, for life to thrive on that planet. Again, another whole couple of hour talk. I'll give a whole course on this over a semester, so it's hard to do justice in 20 or 30 seconds. So I'll jump a couple of these slides, but I think the slides will be made available. These are the kind of distances and the kind of things that we're looking at. And these distances matter if you're a human, because if you're on the space station, we transmit, we have conversations, we transmit video at the speed of light. So the space station, there's not even a time delay. You can talk to the astronauts one-on-one. Um, Once you go to the moon is about in kilometers, about 350,000 kilometers away. And so that's about, it takes the signal to take about a second to come from the moon to the Earth, 1.2, 1.5 seconds. So a time delay of 3 seconds between telling the astronaut to do something and the astronaut telling you that they did it, that's a time delay. When you get to Mars, Mars is far enough away that the time delay can be as much as 20 minutes. And so that's a bit of science for you. But at the same time, if ground control, if the people on planet Earth can't tell you what to do in real time, don't drive into that big hole on Mars. The astronauts are going to have to do a lot of stuff on their own, stuff that they don't need to do right now when they're in the space station, and they probably won't need to do when they're on the moon. But when they're on their way to Mars and when they're at Mars, they're going to have to be a lot more autonomous. They're going to have to do a lot more stuff for themselves um, than they can do than they need to do when they're in the space station. And think about that. There's only four people going. It's probably a 2 year mission. So there's four people who have to do all the jobs. You have to be the plumber, the cook, the electrician, the scientist, the explorer, the spacesuit repair person. All of those different things all have to be captured in those four people. And so this is one of the other challenges, the logistic challenges. You don't even have to be an engineer to solve those challenges. You just have to be good with numbers and logistics and so on. So you bring all of these people together in order to design a successful mission to the moon and to Mars and to other places and to allow and try and anticipate what all those problems are going to be. Rupali, you're going to have to tell me how much time I have left because I think
Yeah,
I'm probably talking too much.
another 4 minutes.
Another 4 minutes. Okay, that's 240 seconds. So one of the things that's happening, and I'm not going to go through all of this. It used to just be governments that did space. Now we're getting into a new world where we talk about commercial space. And so some of these companies you've heard of, SpaceX. And so NASA is now engaging much more strongly with commercial companies. And so the commercial companies are now um, helping provide the capability that NASA needs, but it's their property. In the past, it would go to NASA, NASA would use it, no one else would be able to use it. Now the companies can provide the capability, and then NASA buys a ticket, but they can now sell tickets to other people. And that's allowing more people to go to space and do more things. And there's a huge thriving commercial space industry, which again provides lots more opportunities for people. So we have commercial cargo, so companies who can take cargo up to the space station. We're looking at companies who are now developing their own space station. So when the International Space Station gets deorbited in about 2030, in a few years, there's going to be private companies who will allow you to go and do research in microgravity. And we also have commercial services to the moon. So lots of companies, including some in Houston, will be able to take supplies to the moon and have them ready there for the astronauts when the astronauts go with NASA. And then we're trying to bridge all of that together so that when we do stuff on the moon, we're benefiting everything on the Earth. It's called the cislunar development. And I can't do that justice in 240 seconds, so I'm going to skip, but we can maybe talk about some of that later. International collaboration is very important. You may have heard of the Artemis Accords. You can see India in there. And so these are countries that are signing on to rules of the road and how to do space with NASA. There's a couple of major countries in that you might uh, see are missing, Russia and China being the most obvious ones. But this is trying to get, if you look at some of these countries, you would not think of them as being a space country. India obviously is, but it's because of that commercial capability now that smaller countries are looking to become space countries. And so they're signing up to work with people around the world through the Artemis Accords. I won't have time to talk about this, but one of the big things that's happening in low Earth orbit now is what's called in space servicing, assembly, and manufacturing. There are companies who are looking now to build things in space using resources in space without just building it on the ground and sending it up. So there's a nice benefit to the environmental impact there, but it is also creating a need for the resources from the moon to be brought back to low Earth orbit and to develop these capabilities. And you'll see that growing very significantly, and there's companies in India too doing this across over the next few years. This is just a little bit more detail and in terms of how long some of these things will take. Um, I guess I don't really have time to tell you about Houston in Texas, but the key thing is we have a commercial spaceport that is probably one of the most economically successful commercial spaceports in the world. The Texas government, you'll see right at the back there with a blue tie right in the middle is myself. The Texas government put together a thing called the Texas Space Commission, and they're investing very strongly in commercial space across the state and working with the universities. Rice just got a major award, financial research dollars from them to do stuff about the moon. And then NASA Johnson Space Center is working on with Texas A&M University in creating the Texas A&M Space Institute, at a place called Exploration Park. This is the Johnson Space Center on your right. That big, long, narrow building at the bottom there, that's where the Saturn V rocket is, and then that red circle or red oval is where they're building the Texas A&M facility. It's going to have a football field, and I mean either American football or regular real football, soccer. Uh, they're going to have a soccer field, which is going to be the moon, and a soccer field size Mars. And you're going to be able to drive between the moon and Mars within this facility and test your technologies. That, again, is bringing universities, industry, and government, NASA, together. The Houston Spaceport I've mentioned, this is what the Space Commission is focusing on. And then what Rice is doing, to bring us back to Rice for a second, in that research area, we have a Center for Planetary Origins to Habitability. So we're looking at planet formation and evolution, how they interact with the stars. We've got a Center for Space Technologies, which is focused on the moon, and we'll be looking at creating technologies to allow people to work and get resources from the moon. We have a Center for Advanced Space Sensing Technologies, which is going to allow us to do high advanced state of the art sensing in space. We have some work with NASA that we're doing on human health and performance. So we also bring in some of the sports activity there. And one of the new things that we've done, just for those of you who are not scientists or not engineers, we've created a Space Humanities initiative, which we hope will grow to a center where we're thinking about space policy and space law, and the art and the social sciences, what it means for humans to be thinking about space, different cultures. A lot of the mythology in different countries are centered around the moon or the sun, etc. So we're trying to bring more people into the conversation, and it will also allow us to be a little bit more human, if you like, about thinking about the environmental issues of the moon instead of just digging it up because it's just the moon, thinking about what that means to people, thinking about how we do that sustainably and sensibly. So, international, I've talked about. Jennifer might mention a little bit more about Rice's global outreach, but we have a US-Japan Space Forum every year, a National Italian Space Day every year, and a lot of different activities that we're really excited on. So I'm going to finish with this, Rupali. I know I'm over, but I want you to think about this. We often think about space as somewhere we go. We send up a rocket, we send up a satellite, we send up a rover, we send up whatever. But it's not just a destination. It's a resource. It's a resource for information about the planet Earth, about the universe. It's a resource for if we were to mine water on the moon, we can then have an opportunity to build and create things in space for space instead of relying on the Earth. It's also a resource for power and energy from the sun. If we can mine an asteroid and get materials from asteroids, that's something else that can benefit us on Earth. And then that middle one is the key one. If we're going to solve the problems that we're trying to solve for space exploration, the moon and Mars in particular, we have to bring in smart ideas, not just from space people, but from people across all of the disciplines, from life sciences and health, from energy and energy transition, renewable technologies, all of those things. We have to bring those ideas in so that we can be effective in going to space. And then how can the sky be the limit? There's footprints on the moon. So there's no end to your ambition. Your generation is going to live in a very different world from mine, and you're going to help shape it, just not necessarily by becoming space people, but by thinking about some of these challenges and thinking about some of these problems that your intelligence and your passion can bring and solve. So again, that was a quick run through space. So I appreciate your time, and I think Rupali, we can move to the next section. I will stop sharing so that Jennifer can share hers, but hopefully we'll get some good questions and we can talk about those in a little bit. So again, thank you for your time.
Thank you so much, Professor. It was lovely hearing from you. And as you rightly mentioned in the beginning, that 40 minutes are not enough. They are never enough. But then, just to make sure that the students get some idea about space science programs, and I could see that there are so many questions that the students are writing. And the ones who have little knowledge about space, they are actually responding to their fellow friends as well. So that is the best part of having these masterclass, where we are able to have students of the like-minded students of the same interest who have joined, and they're also responding. Jennifer, you can share your presentation now. And
Mhm.
students, just hold on for the next 5 to 7 more minutes. Jennifer is going to give you information um, her
Our
about the
university.
Rice University, which is one of the most sought after university by Indian students, which has a lot of excellent programs. You can check when you go back, and after the session is over, you can check on their website and look at their programs. And if you have any questions, we will share Jennifer's email ID also. You can write to her. Over to
Yeah,
you.
thank you so much. Absolutely. Thank you, Dr. Alexander. That was such a great presentation. I learned so much. I learned a little bit about rice that I hadn't known before, and I learned a lot about space as well. As he mentioned, there's no one right path, right? There's plenty of ways to do the things that you love. Not everyone is really interested in a PhD degree. Maybe people aren't interested in graduate school, but some of what I will talk about today is graduate programs. So if I can plant the seed, if you're not quite ready for grad school, and maybe you're thinking about it far in the future, just know that it is an option for you, and Rice is a great place that will support you. And so I'm going to go ahead and share very, very briefly about Rice's grad programs and maybe some initiatives that will help you when you're thinking about applying to grad school. So, why graduate study at Rice? As mentioned, we have a lot invested in research. We are, as Dr. Alexander said, a small but mighty university. We have about 8,000 students, 4,000 grad and 4,000 undergrad, roughly split down the middle. And in the research enterprise at Rice is comprised of both the grad and undergrad experience. We have undergraduates that do research. Our graduate students certainly do a lot of research, and of course, our faculty as well. And so we are very invested in moving the needle for humankind, making sure that we are doing things that will help humanity in the future, but also increasing our human knowledge, learning things about the world that no one else has learned before. And so that's really what we're trying to do here at Rice. If you're thinking about graduate study, there are master's degrees and PhD degrees. If you're thinking about a research career, a PhD degree could be a great choice for you. So I encourage you to think about that. Our stipends for PhD students start at $37,000 a year. And the reason that you get a stipend is because it's kind of like a paycheck. You're going to be doing research work for the university. And so we want to make sure that we compensate you for the work that you're doing, the ideas that you're generating. Another thing I would say about Rice, I already mentioned that we are a small but mighty institution. We do have a very collaborative environment. And so many universities across the United States can be very competitive. And Rice is really more of a work hard and work together as a team to get things done kind of place. And so we feel that you will find that here at Rice, this community and this culture of care that we have at our university. A little bit about Houston, Texas. So, we are the fourth largest US city after LA, New York, and Chicago. And we are a global hub for a lot of things. You've heard about the space industry today. We're also a global hub for medicine and energy. We have the largest medical center in the world, and that's a lot of opportunities for collaboration with doctors and researchers there. And as Dr. Alexander said about the space industry, it runs the gamut of fields. Anyone from humanities to music to natural sciences and engineering, all of these these folks are working on things like aerospace, working on things like medicine. And so while Rice doesn't have a medical school, we do a lot of research related to medicine as well. And we have a very highly ranked bioengineering program also. Houston is a very diverse city. Most of the people here, you will get exposure to people from lots of different countries. There's 145 languages that are represented here in Houston, and about 40% of residents of Houston speak some other language besides English at home. And then we do have a strong residential community at Rice as well. So for both undergrads and graduate students, we have housing on campus, and those are really places where you can meet your friends and build tradition and build community there. And we have a really great place, a great team that will support you while you're here at Rice. A couple things that I wanted to mention. We do have fee waivers available for PhD applicants. And so you are welcome to sign up with this QR code to get more information. This will open October 14th and it will close November 1st. We will have some basic eligibility requirements for you to meet. But this is a great way if you're thinking of applying to different schools in the United States and you want to make sure that you save a little bit of money because those applications can be expensive. We welcome you to participate in this program for PhD applicants in particular. If you're thinking about applying to grad school, I would love to talk to you more. We have many, many events coming up. We also have graduate student ambassadors that are ready to talk to you. And they're from all over the world, all different fields of study. If you have an interest in space, but you might be thinking about studying something else, you will find somebody to connect with through our graduate ambassadors. If you want more information from Rice, you can scan the QR code here and fill out your information to get all of the things that are coming up. So all the events that we have coming up, we'll be sending out emails about those, including events like this one with Dr. Alexander. We will have more events with faculty coming up this fall as well. And we really value your questions. And so Amitha and Rupali, they said that they were going to share my email. I'm going to go ahead and put it in the chat as well. You should feel free to reach out to me anytime with questions that you might have. Doesn't have to be Rice related, can be things related to graduate study or study in the United States. I'm always happy to point you in the right direction. I think I made time okay, so I'm going to go ahead and stop here because I know you'll want to get to the Q&A for sure.
Yeah, thanks, Jennifer. And I think we have a lot of questions, but we'll try to answer as many possible. So the first question for you, Professor, is what what subjects should students focus on if they want to pursue a career in space?
Yeah, so, and I've also been while Jennifer was speaking, I tried to answer, I started at the beginning and tried to type in some answers. So forgive my little joke about the wormholes. But anyway, no, I think one of the areas is obviously mathematics. It covers a lot of different things. And I know India is very good at mathematics. So I think that um, math is a key thing. If you're interested, I think one of the things I tell my own students too is it's much better to do something you're passionate about than do something perhaps because your parents tell you to do it. I didn't say that if there's any parents listening, but I think if you're really passionate about something and you have the skills, then you will do it well and you will enjoy it. I've been lucky in that I've always had the opportunity to work on something I'm very passionate about, and that's worth more than any money they can pay you and worth more than any other thing. But to prepare yourself for it, you need that basic skill set, and I think mathematics is key. And then depending on your specific interests, any other science or any other engineering attributes you can get. So I think for the aerospace side of things, those would be the key things to focus on. It doesn't exclude you if you did something else, because there are always opportunities that come along later.
Yeah. So the other one is, what advice would you give to a student who wants to study aerophysics?
To study aerophysics?
Right.
Well, I mean, I think find a good school, right? Obviously, going back to what I just said, if that's if I understand what you mean by aerophysics, I mean there's a lot of different physics that gets applied in aerospace engineering, for instance, aerodynamics and things like that. Those are heavily on the math as usual, but they're also heavily on computing and modeling. So again, developing some computer skills and thinking about how you model and do what we call physics-based modeling. And so you put in a lot of those physics equations, that we need for example, for aerodynamics. So again, those basic skills are the things at your age that you bring. And once you get to university, you will learn that there are other areas, and some of them will be more interesting to you than others. And you can pursue them as you go. You'll always have opportunities to grow as you go through your careers. So don't think you can do it all at age 16 and that's you for the rest of your life. We're constantly learning as we go. I learned something. I mean, even in Korea this week, I'm learning new stuff. So I think you always have to be open to that, but you want to give yourself the best foundation, and that comes from doing well in school, really, high school
Yeah.
and college.
So every day is a learning day, and
Yes.
all these and the COVID has actually taught us how to upskill yourself, and other than your um, uh, academics only, your skill development is very, very important, students. So keep that in mind. There's another question, Professor. So the question is, in the long run, for about 15 years from now, which will be more in demand, energy engineering for sustainable fuel or aerospace engineering?
I think the we need the energy sustainability. I think obviously we need to move away from the oil and gas and the hydrocarbons. And there's a lot of focus of that in Houston and Texas, and the technologies that are being developed there are really important. We've got the renewable technologies, but we have to make renewable technologies more efficient as well. So I think that is going to benefit. People see that as a more direct benefit to everybody on the planet than, for example, exploring space. So um, as much as I think we can do both, I think the energy sustainability and solving the world's energy problems, I think, would be something that was still going to be a problem 15 years from now. I'd like to think we'll be on the moon 15 years from now and thinking about Mars, but I think the energy problem, if I had to pick one of those two, that would be the one.
Okay. Um, what is the biggest mystery in space that scientists are trying to solve today?
If I knew that, it wouldn't be a mystery. Um, I think, I mean, we're trying to understand essentially, there's still a lot of depends what scale you go to. For the sun, we're still trying to understand why the atmosphere of the sun is so hot. But in the bigger scale, with James Webb Space Telescope and others, the universe used to be stars and all the stuff we could see in the sky. And then we realized that there was a thing called dark matter, and it was matter that had a gravitational effect, but that we couldn't see. And so it turns out that was most of the universe. And now we have a thing called dark energy. And dark energy takes up about 63% of the universe. Dark matter takes up about another 30 something percent, maybe 20. Anyway, and then the stuff that we thought as it makes up you and me, that's only like, something like 6 to 10%. I can't remember the exact numbers. So that's a big mystery. What is that material? We don't know what dark matter is. We know it's there, but we don't know what particles make it up. Dark energy, maybe it's a thing that Einstein called the cosmological constant, but it's making the universe expand faster, which is counterintuitive to gravity, which tends to slow you down. And so these are some big, big mysteries about the whole universe that we don't know. And we're learning more information that makes what I always say is science isn't about finding answers. Every time you try and get to an answer, if you're doing your science correctly, it's creating new questions. That's how science moves forward. And so we're generating an awful lot of new questions about the things we don't understand.
Right. So you spoke about James Webb. So there's a question on that. What discoveries from the James Webb Space Telescope have astonished astronauts like most?
Well, again, I don't like saying best and most because there are many different types of astronomer learning different things. We're learning a lot about early stars and early galaxy formation. We're using James Webb to look for planetary atmospheres and look for signs of um, I mean, science for life, but that's challenging in itself. But we're looking at if there's oxygen in the atmosphere, for example, could that imply that that planet has a lot of life, at least plant life, if nothing else? So I think there's always an open end to these discoveries, right? So we're learning more about the universe and how it expands. We're learning more, but that's adding more questions. Is can we understand that? It's one thing to see it; it's another thing to understand it. We're learning more about galaxy formation. We're learning more about distant galaxies. We're learning more about planets, and so on. So it's just a whole sweep of things that the James Webb is allowing us to do. And the key thing I'll tell you about James Webb, this is where science and engineering comes together. All those science questions are very important, but you could not launch James Webb the way it is. It had to have very, very clever engineering in order for it to work, and everything worked. This is something I learned at working in industry is the science. I'll tell your folks what I tell my students every year when they come in. One of the things I learned at Lockheed Martin is when a scientist like myself goes in and talks to the engineers and tell them what they want to do, once the engineers stop laughing, they tell the scientists what they can do because things cost money. You can only have so much power in space. You can only send up a certain size of things. But I think the scientists and the engineers together make the science happen, and I think that's key.
Perfect. This is an interesting question. Are there solar storms? How do scientists predict solar storms?
Well, we don't do it very well.
Hmm.
One of the things we try and do, yeah, there are definitely solar storms, and this is that movie showed you some of the aspects of them. What we try and do is look at the sunspot is an enhanced area of magnetic field, and that's where the energy is for the solar storms. So we try and look at the distribution or what the structure in the sunspot. You need a lot of magnetic field because you need the energy, but the magnetic field has to be complex. It can't just be a nice simple bar magnet like you might buy out of a store. It has to have much more complexity to it because you want to be able to take a bunch of time to store a lot of energy, but then it has to be released very quickly. So what we try and do, and we're getting better at predicting whether an event will happen, but we're not very good at telling you what that event is going to do. So for instance, these storms affect satellites, but only if they come to the Earth and they interact in a certain way with the Earth's magnetic field. We know a storm is coming, but we don't know if it's going to have that kind of problem. And that itself, if you tell the whole spacecraft industry that there's a storm coming and they need to put their spacecraft in safe mode, they lose a lot of money. And if nothing happens, they're not going to believe you. So we're trying to get the science right. So it's very, very complicated to predict an event, to tell you what the event is going to look like, and then to tell you what it's going to look like when it gets to the Earth, and then understand how the Earth is going to respond. So that's why it's very, very difficult to predict the impact. Well, it's getting easier to predict an event. One of the things we do for astronauts, for example, in space weather prediction, is giving them a warning that maybe they shouldn't be taking a spacewalk because the spacesuits don't protect them as much as the space station does, for example. This is going to be a big problem on the moon and Mars.
Perfect. And I think we can take one last question. What are primordial black holes? This is
You
one.
can take another one because I answered that in text. Stephen Hawking came up
Okay.
with
Okay.
primordial black
Perfect.
holes.
Probably I missed that. I think we have to conclude this session. I mean, you feel like hearing and hearing more and more. Um, Thank you, Professor, for joining us. And I'm sure the students enjoyed this short but excellent talk. And thank you, students, for joining in from different parts of India. We will try to make sure that we have more and more sessions in the coming months and make sure that these master classes give you a lot of information. Thank you so much. Thank you, Jennifer, for joining. And Professor, in case there are students may want to write to you, just if you have some time, they can write to us, and we'll further write to you with the questions. Thank you so
I'll be
much.
happy if I can.
Yeah, yeah,
I'll be
we
happy to answer
understand
if I
that
can.
you're all, yeah, so we will make sure. Thank you so much, everyone, and have a wonderful uh, week ahead. We have a long weekend now. We'll reopen. So tomorrow is June 19th, and we are closed. It's an American holiday. Jennifer, thank you so much. We will see you soon. Thank you.
Thank you. Thank you, Dr.
Thank you. Thank you
Alexander.
all.
Have a great day or
Thanks,
night for
Jennifer.
you, Dr.
David, please.
Alexander. Have a great
Yeah.
rest.
Thank you all.